completing the square. So first of all, what does that even mean? Okay, in this context, it means this. This thing right here, x plus 5 squared, we call a perfect square because it's something squared. You've known what perfect square means your whole life. You know, 4 is a perfect square and 25 is a perfect square. And this is a perfect square. It's x plus 5 squared. Now, the next thing is a perfect square trinomial. I get that from multiplying this out. Why didn't I put x plus 5, x minus 5? That's not squaring something, is it? Squaring something is multiplying it by itself. So this gives me x squared. What's the middle term going to be?
5x.
5x and 5x. So 10x plus 25. All right? So this is a perfect square. This is a perfect square trinomial. It's the thing I get, the trinomial I get when I multiply out the perfect square. Okay, excellent. So that's like vocab. And so, here we go. If I have x squared plus, I don't want to give you one that you're going to do in a minute, 8x, what would have to go here, like a box from the olden days in year 2, what would have to go there so that when I factorized this, I get a perfect square? Just stop for a minute and have a thought. Don't just raise your hand yet. Not yet. Everybody get a number that they think would go there so that when they factorize, they'd get some perfect square that would be that. I hear people whispering it. 16? How'd you get that?
Half of 8.
Half of 8
Squared.
squared. Is that right? So what does it factorize to? 4, yeah? Is that all right? Okay?
How do they know to do that?
Okay, this is what they did. They said, you know, up here it turned out that I had 5x and 5x that added to 10x. And so I must have had something x and something x the same that added to 8.
yeah.
So they cut 8 in half, and then they squared it to get that end one. Right? So completing the square, isn't that what you just did? Okay, so here we are in reality, and I'm on a test, and it says y equals x squared plus 10x minus plus 23, and it says, please graph that, and you're like, that's a crazy thing to graph. I can't factorize that to find the x-intercepts, and you know what I mean? Okay, so it might say the directions graph by first completing the square. Okay, so just put your pencils down for a minute, and here's how it goes. I ripped these two off, and I put a space there for my completing the square business, and then I put my 23 there, and then I have to also subtract that thing off. Why do I have to do that twice? Add it on and take it off. I can't change the value of the expression. I can't just add something on, right? I can't just do that. I did it up here because I said I'm filling in a box, right? But this is like, I want y to actually equal that. I want it to stay that value. When I put 1 in for x, you know, I want it to be 1 squared plus 10 times 1 plus 23. I don't want it to change its value. So I'm going to complete the square. What goes here?
25.
Yeah, 10 over 2 squared, yeah? 25. And so I have to put 25 here.
Almost 5 minutes.
Longer. So that bit there is the square part. So it's the y equals x plus 5 squared. Where'd I get that 5?
Half 10.
Yeah, it's that. It's that. Okay? And then I just add these two up, and this is, going to be something else in my equation. That's something else. That's -2, yeah? What's the turning point of this parabola? You know this? Yeah, right? So it's -5, -2. So now I have this, and it's also called, this thing about completing the square, turning point form. So that's when I use it. When I need to find the turning point, I do this completing the square thing, and it helps me. Because now I can see the turning point, and also from before, I can see the 23 up there, the y-intercept. So if I needed to graph, I'd grab my ruler, and I'd go like that, and I'd go, okay, -5, -2, and I'd put my turning point there, and I'd go up here to 23, and I might put a point that's kind of symmetry there, and I'd, oh, it's so bad, girls, I'm sorry. I'd draw my parabola.